Welcome to Dark Chatter episode 3. Joined this week with Joe Chen from UNSW.
Hello.
Very far away. Hope you traveled well.
That was a rocky bus ride.
Yeah, they always are rocky bus rides. So in case this is the first time you're tuning in, what we're essentially doing here is having casual conversations about recent physics papers. And today, Joe's going to take us through his new paper, One Line to Run Them All, not to rule them all. Super easy massive neutrino linear response in n-body simulations, which is a great mouthful of a title. Love it.
Had to get all the keywords in. I think that was the main concern.
Well, I'm a big fan of having like a sort of fun title and then the technical thing afterwards, just to get everyone's attention. I'll always click on those over something really boring. So that's a good strategy if you're out there listening and you want me to read your paper. All right, so maybe let's just start with an introduction. Tell me about your research interests. What are you doing?
Okay, well, I started off working in neutrino particle physics, like neutrino theory. But then when I started my PhD, Yvonne offered me this idea of doing a more numerical, large code structure related simulation work. And I thought, why not? I'll take it up on it because the way she sold it to me was that it is meant to be a skill that's highly valued in applying for postdocs, because a lot of people have a lot of ideas on large scale structure, but not a lot of them wants to like kind of get their hands dirty with this numerical simulation stuff. So I thought it kind of both touches on the interest of neutrino physics that I always enjoyed, and at the same time seems rather employable. So can't lose.
Yeah, employability is something we all worry about these days, I guess. So if you had to like pitch this paper to a newspaper, I don't know, someone who doesn't really know that much physics, what would your summary of this paper be?
Okay, so to a newspaper, that's kind of...
Or just like, give me your elevator pitch, you know?
Yeah, okay. Funny enough, actually, this paper is about neutrino linear response, but then you don't actually pitch this to neutrino physicists, because the idea is to actually... because we know neutrinos in cosmology has like a lot of large impacts on how structure forms and the history of the universe. So they definitely have to be considered. So what this paper allows people to do is to include neutrinos in literally the easiest way that I could think of. And it will give them the correct answer for other kinds of work. Say if you're a person working in hydrodynamics on simulating like gas physics and something like that, but you still have to worry about neutrinos, but you don't want to dedicate like thousands of computation hours on getting it correct. You just want it to be like good enough. And this offers a more than good enough way without tying any more resources down than necessary. So it's meant to be like aimed at people that need neutrinos to be included, but don't really want to waste more time than necessary on getting them exactly correct.
So you're using your expertise to sort of fill in the gap that other people probably don't care enough about.
Yeah, exactly.
Okay, cool. And I guess your expertise is neutrinos. Can you just like give us a quick intro to neutrinos? Why do I care that they may or may not have a mass? Like, what's going on here?
Okay, so in physics, there's plenty of new ideas getting thrown around all the time. Like everybody thinks about possibilities and what new models you can come up with. And neutrinos kind of fall into like a different category where we know they definitely exist. They're in the standard model.
Yeah.
But then experimentally, we also know that they definitely have mass, which standard model don't allow them to at present in this present form.
Yeah, I'm sure there's some people who'd argue with you on that one.
Yeah, okay, but the majority consensus is that it is possibly the lowest hanging fruit when it comes to like new physics, because it's a complete necessity that you must come up with some way to explain why neutrinos have mass. So in that case, then I think it's like the most min-max if you want to like, because sometimes when you invest in new theory, who knows, maybe in 20 years time when the experimental data comes out, you find yourself on the wrong side of the fence. But in this case, it is kind of like a definite payoff that we do have to study every new kind of physics with the neutrino mass included now, and not just kind of ignore them and pretend like they don't exist like we do with standard model for so long.
I guess it's like we have neutrino oscillation experiments. It needs explained somehow.
Yeah.
This is sort of how I feel about black holes as dark matter. You know, like that's the one that we actually have. Come on, why are we? Anyway, this is my talk. But okay, so neutrinos seems like they have masses. That's probably an uncontroversial thing to say. Maybe, I don't know. How does this possibly affect cosmology? Like, why should these people you're helping out care?
Oh, hugely. Because the weird thing that we're doing large-scale structure cosmology is you fix how much matter is in the universe, like massive matter, so we're ignoring radiation and stuff like that.
Yeah.
We fix how much matter there is in the universe depending on how much of it there are today. And then you extrapolate that backwards in time and they get to do whatever they want in the early universe. So if neutrinos have mass, that means today they count as massive particles and they take up part of this budget. And then with the fixed amount of total matter budget, then that means you get less cold dark matter in the entire universe budget.
Yeah.
So then when you wind the universe back in time when temperatures get higher and higher, cold dark matter still behaves like matter, so they cluster and they form structure as they should. But then neutrinos, because they're so light, by the time you get up to early times with high energy, then they start to behave like radiation. So you're losing a part of your matter budget at early times that don't actually contribute to structure formation at all.
Okay.
So that compared to massive neutrinos means that you get a lot less growth that's possible compared because in a massive neutrino in cosmology, everything's called dark matter and they're always contributing to clustering, whereas now you have part of them that is masquerading as matter now, but then they aren't actually pulling any weight at early times.
Right. So you're saying I expect less structure formation?
Yeah, usually people say massive neutrinos affect large scale structure by dampening the matter power spectrum, like essentially smearing out some of the stuff. I don't know if, can we show pictures here?
Yeah, we'll flash up on the screen, but you can just show me.
One of the snapshots that we took with our simulations comparing massless neutrinos versus massive neutrinos, and you find, let me see if I can find this. There it is, yeah. So you get a lot of like very well defined structure in a massless case because structure has been growing in the entire history of the cosmology. But then with massive neutrinos, you see it's a bit smeared out. Like things haven't had enough time or enough opportunity to really cluster tightly. So things are kind of a bit more spread out, and you get a fuzzier looking universe.
Right. I'm sort of vaguely aware of these issues in structure formation and simulations, like not having enough dwarf galaxies and stuff. Does this solve this problem or make it worse? Or?
No, it actually does, because you wipe out some of those small scale structures. Okay. So some of the smaller dwarf galaxies don't get a chance to form. So it does push in the right direction for the small scale crisis.
Okay. Yeah. So yeah, that's interesting. So the people running the simulations, those errors might be because they're not putting the massive neutrinos in correctly. Or is that a bold claim?
That's a hard question to answer, because down to that scale of like our Milky Way and like around us, the local group, you start touching on things like baryonic physics and gas physics, where
more stuff we don't have.
Neutrinos definitely have to be considered, but then there are so many other things that I can't really make any claims on this.
And then I guess my question following on from this is this the first time people have been putting in massive neutrinos into simulations? And if it is, why not?
No. People have been trying for a very long time. And the reason we call this super easy is because it has always been a massive headache for everybody that's tried.
Right.
So this is like one of those things where people, when they do simulations, they ask themselves, is it worth the headache? Can I live without massive neutrinos? And if the answer is yes, then I'll throw them away because it's just too much effort. So now we're offering them like kind of an alternate method where now they have no excuses to say we don't want to think about neutrinos, because now we simplified it down enough that everybody can do it. But people have definitely been trying for almost 2 or 3 decades now. Like people been putting massive neutrinos into simulations, but no one has reached a consensus on how or what is the best way yet. So this is still like a bit of an ongoing thing.
Right. So you're just trying to make it easy enough that everyone can just do it.
Yeah.
Right. What makes them so hard to put in usually?
So the reasons that in simulations, usually if you have just cold matter, they're quite easy because they don't shuffle around. They sit very still. So then at the early universe, you place them down nearly homogeneously, and they might have some disturbances and fluctuations here and there. And then you let them go, and then they just gravitationally cluster towards where the high densities are. But with neutrinos, because at early universe at high temperature, they're very thermal. So that means they have an inherent velocity. They're kind of zooming around as well as being gravitationally attracted. So you essentially have to consider how many particles you need to capture this space-based density. With cold dark matter, you just need 3-dimensional spatial sampling. You just have to sample enough places. Whereas for neutrinos, you have to sample enough places, and at every single place, you have to then sample another 3 dimensions of velocity dispersion.
Okay.
You have to sample the whole Fermi Dirac, and that costs you just way too much if you do it naively. Like even the biggest supercomputer in the world can't handle that kind of calculations right now.
I see.
Yeah.
So, I mean, I confess that actually, almost nothing about n-body simulations, and it's always been that sort of thing where I have this like skepticism in my head. You sort of have these particles in a box and you're simulating them, but the particles are what, like 10 to the 6 solar masses in size?
10 to the, I don't know, 26?
Sorry, wow, I was way off. Okay, and you're attaching particle physics things to like neutrino masses to these.
Yeah.
And I've never understood like how do n-body simulations work with particle physics? Like how do you mesh those two?
Okay, so the Boltzmann equation is where the gap kind of the two gets to meet each other.
So what's the Boltzmann equation?
The Boltzmann equation basically. So if you describe your particle, if you have a lot of like enough to fill the universe, then you can kind of squint hard enough that they suddenly become like a continuum fluid rather than individual particles kind of dotting around.
Yeah.
And now you can describe this whole distribution of your particles as a phase-space distribution function in the Boltzmann equation. And now you can start using fluid dynamics to solve these equations.
Yeah.
So you don't want, you can then essentially treat them as one gigantic blob of fluid that's interacting, first of all, under self-gravity, like gravitation attract each other.
Yeah.
But then you can then pull particle physics into this because on the right-hand side of the Boltzmann equation, where you have the collision term where the interactions happen, that depends fully on particle physics.
Yeah.
But then you can easily attach that into the whole fluid description, even if you don't have individual particles resolved.
Right.
So you can still think of saying, if I have one gigantic blob of a lot of neutrinos, on average they interact in this, some decay or like some secret interaction with dark matter, for example, then you can still statistically talk about it, even though you don't see individual particles. Yeah.
And is it sort of like multiple fluids which interact, or is it treated as one big thing, or how do you do this? For different particle species, I mean.
The first stage of the n-body simulation, when people just start, they usually run just lambda CDM cosmology, so then lambda's cosmological constant doesn't really manifest. So all you're doing is cold dark matter particle.
Right.
So that's just
one big fluid.
Yeah. But then once you add neutrinos in, then you have the cold dark matter fluid and the neutrino fluid. They individually self-gravitate, but they also influence on each other.
Yeah.
So this is what like the linear response story. The response is the interplay between the two fluids, how they influence each other.
Right. So that's a good segue into the next sort of level of confusion question I have.
Yeah.
There seems like there's a separation between like linear approaches to figuring out the evolution of these fluids and non-linear. And my question is like, what is like the piece of physics that makes something non-linear versus linear? Okay,
so it's like any perturbation theory. You have some parameter that's small, and then you can expand on that.
Sure.
So in the universe, we talk about the average density of the universe.
Mm-hmm.
So you have, at the very early times when the universe is basically close to homogeneous, then you just have a well-defined density in the universe. And then because some parts will be slightly denser and some parts will be slightly more sparse, because it's seeded by the primordial power spectrum.
Yeah.
So then you talk about how much above and below the average density you are.
Yeah.
So this is a density contrast.
Yeah.
So if that parameter remains small, then everything's perfectly linear, and then you can perturbatively expand it and solve it with perturbation theory.
And that's an analytic calculus.
That's
in
some limits you can get analytic solutions. Yeah. And then when this density parameter, as the universe evolves and these little clumps starts gravitating towards each other, so then you get larger and larger clumps that are starting to be way higher than the average in density.
Yeah, I see.
So then once that approaches 1, then suddenly your linear theory breaks down, and then you have to go to nonlinear perturbation theory. And for n-body simulation, it reaches into a realm where it's so far nonlinear that even nonlinear perturbation theory breaks down. So it becomes non-perturbative altogether.
And so, I guess my question then is, what is it specifically you did to speed up this nonlinear, whatever you've got going on?
Okay, so
what's your breakthrough?
So this might be a bit long answer. So
yeah, well this is the meat of it, I guess, right?
So at the beginning they simulate neutrinos as just particles by naively putting them in the same way that you put in cold matter particles, and then see how they evolve inside a box. And they quickly realize that they don't have enough computational juice to actually do that properly.
Okay.
So then people start thinking, okay, how the particles in the simulation actually influence each other? And they realize it's just via gravitational potential.
Mm-hmm.
So then, rather than having physical neutrino particles or like equivalent n-body simulation blobs in there influencing the gravitational potential, how about I just try to solve a semi-analytical solution on how the presence of neutrinos would modify the gravitational potential.
Okay, right.
So then you just have a simulation with only cold dark matter particle physically existing in the simulation, but then at every time step, when you decide to move them, when you look at the gravitational potential and trying to figure out how they should move from that point onwards, you then kind of cut in there and then add a neutrino contribution at that stage. And
Just
then,
with like a little equation.
yeah, with an additional line in the modification of the potential. And then the dark matter particle will then be tricked into moving as if neutrinos were actually present, but they aren't physically there.
So is this then only a linear sort of thing? Because I imagine they would, once you change dark matter, that should affect the neutrinos again back and forth, right?
Yeah, exactly. So at the beginning first, Jakob and Steen, they did this fully linearly. They just had neutrinos kind of, the equations are involved in like a Boltzmann code in the background, and then at every time step, they just kind of step in and add their contributions, and the dark matter will respond accordingly.
Sure.
And then later they thought, yes, well, the evolution of neutrinos density should be affected by how the dark matter is evolving, especially at late times when dark matter start evolving non-linearly. You will deviate far from the linear Boltzmann treatment of the neutrino evolution that you do.
Yeah.
So Simeon Burton, that they thought this way to have the neutrino equations be solved at every single time step. So you feed in the real dark matter simulation results into the neutrino equations, evolve them, and then use the evolution result back into simulation to change your gravitational potential. And this interplay kind of happens throughout the entire simulation. So you have the neutrinos affecting dark matter then tells neutrinos how to evolve, and this goes on and on. And what we did was basically coming to do this exact same thing, but simpler, because the old linear response method with Simeon Burton, it required you to actually integrate over the entire history of dark matter evolution. So you have to, in your computer program, save the entire history of the dark matter particle in that box. And that quickly could become like either hard to implement or just cost a lot more memory than you really would like to spend. So we came up with a semi-analytic equation that doesn't actually require you to store anything, doesn't require you to calculate, doesn't require you to like remember what the dark matter is doing. It just has to know what the dark matter is doing right now at this moment, and then through one polynomial evaluation, it gives you the neutrino density at that time.
So how did you guys come up with this semi-analytic thing that's so brilliant, like just works perfectly? What was the breakthrough you had that allowed this to exist?
I can't take credit for that. Yvonne came up with this, so Yvonne's my supervisor.
Yeah.
So she came up with this almost 15 years ago.
Wow.
She wrote a paper where she wrote down the Boltzmann equation for neutrinos in the presence of dark matter and everything else.
Mm-hmm.
And the equation was a complete mess, like, as you can imagine. Full general Boltzmann equation are very rarely you'll find a closed solution for them.
Yeah.
But then she thought, okay, what if I just look at the very small scale, so for like k becoming very large, and like a large k limit, what happens to the Boltzmann equation? And it turns out it actually simplifies to a very simple inverse 1/k² relationship between the dark matter density and the neutrino density.
Okay.
And then when you look at the very small k limit, so like the very large scale limit of the universe, then like you can intuitively kind of see that neutrinos on very large scales should evolve the same way as dark matter, because at scales large enough, with your gravitational potential strong enough, everything's going to fall in. I don't care how quickly you can run away from it.
Yeah.
Everything's going to get gravitationally attracted towards the well, so then neutrinos and dark matter kind of evolve identically. And then in the equations, you actually see the same thing. If you take the small k limit, the large scale limit for the Boltzmann equation, it reduces down to the same evolution equation as the CDM particles. So with these two limits well defined and well solved for properly, she then thought, okay, nothing weird should happen in between. So I should be able to just interpolate between these two limits.
How confident are you in the should?
I mean, it's not hard to check, so I suppose the confidence is given to you by the results. So if you find an interpolation function between the two limiting solutions, you apply this to both the linear and nonlinear result, you realize that for cold dark matter solution, you get the answer within like 0.1%. And then for total matter, you get the answer correct within 1%. So,
what does it mean to be correct? Like, what are you measuring this? How do you check the correctness of this? Yeah.
Okay, so in linear thing, we can check it quite easily because you can solve a Boltzmann code linearly with massive neutrinos included and solve it properly.
Yeah.
And then you then compare that to the result given to you by this interpolation function, and those two agree with each other within 1%.
And that's the really long, annoying to compute thing.
No, the linear Boltzmann code is fine.
The linear one's fine. Did you check it against the long, really difficult to compute one?
Yeah, we actually did. So in this one, we took our approach and we simulated it with the interpolation function.
Yeah.
And then we also ran a simulation with Simeon-Bird's method. So the old, not old, it's still current, like the state of the art, the long method, and both of them agree within 1% again.
That's pretty good, yeah.
Yeah, so we thought like, okay, if you are a simulation person that's running something and all you care about is the cold matter and all you care about is the lensing or something like that, then this gives you a perfectly fine result.
Yeah.
The shortcoming is that it doesn't actually give you the correct result for neutrinos. The neutrinos are kind of off by about 20%.
That's sort of amusing, I guess.
Yeah, so it's kind of funny that like the focus on neutrinos, but then at the end of the day you get the neutrinos more wrong than you get the total matter.
Yeah. I mean, I guess this is dark chatter, so we care about the dark matter here more. Don't know if the neutrinos can be the dark matter, so...
In that case, then this is perfect for everyone.
Yeah, perfect for the audience of this, perhaps.
Yeah.
Are there alternatives to this that are even close to as good? Like, what else would you do?
Yeah, there are actually plenty of alternatives. So, the state of the art is like I said, the Simeon-Bird's linear response. So that one's integrating over the history of the dark matter history and then finding the neutrino density every time step.
Have you showed them your one yet?
I don't think so. I hope they have read it sometime. It's been out for a week or two.
Okay.
Maybe it caught their attention. But yeah, there's also another approach which is a post-processing approach. You run the simulation with just cold matter particle and you don't actually do anything else to it.
Yeah.
And then at the end you solve an equation after the fact. And then that tells you how to displace the cold matter particle in your final snapshot to incorporate the effect neutrino would have had cumulatively over the entire runtime of the simulation. So it's kind of like a post-shuffling to make sure that everyone sits in the right place.
And that works?
Yeah, that works. That works as well. And then there's also another method that's actually quite new that does the same way as perturbation theory does. So you have, in normal perturbation theory, you have a distribution function, you have the background part plus a perturbed part. So rather than simulating the entire distribution function, they only simulate the perturbation and they leave the background part Fermi-Dirac and evolve it as if they know the analytic solution for it, which is a fairly good approximation for small neutrino masses.
Okay.
So there's a couple of competing lists, and then we also wrote another paper on a different method as well.
Oh, nice.
And released it
at the same time.
Yeah. So our other method is much more complicated, but it does have a better approach because it does get neutrinos more correct, and it allows you to expand on it to do something called a hybrid simulation. I don't know, do you have time to talk about the hybrids?
We've got 6 minutes left, so you can go quick on it. I'm just mostly impressed you got out 2 30-page papers. Did you write all this?
No. I'm always
an
important contributor to this as well.
Yeah.
But yeah, the other method is very good because at the end of the day, linear response is still linear, and linear theory will break down eventually.
Sure.
So at some point in low redshift, you still want to, if you want to get the neutrinos absolutely correct, you still have to convert into fully particle simulations at some point.
Yeah.
And that is very hard to go from a linear response, like a perturbation theory, to full particle theory. So this other paper that we wrote basically allows for this interface to happen without too much headache, because we basically segregated a neutrino fluid into a whole bunch of separate individual fluids of different momentum. And we know that the faster ones will still swim around and run away from potential as fast as they want, and they're not going to bother about clustering. But the slow ones will get pulled into potential.
Right.
So that allows you to know exactly which ones you need to convert to particles and which one you can leave them alone and then stay perturbations.
Right. So you sort of slice up this velocity dispersion.
Into
exactly. 2 realms.
Yeah.
That seems clever. Yeah.
Yeah. So both of them serve very different purposes. One is for people that don't really want to know about neutrinos but needs to include them anyway.
Yeah.
The other one's for people that really want to get neutrinos correct, and it allows you to do hybrid simulation where you can actually get a nonlinear power spectrum for neutrinos.
Yeah. Why would I want to get the nonlinear power spectrum for neutrinos?
Well, the easiest answer is for experiments like Ptolemy, where they are thinking about detecting relic neutrinos on Earth.
Right.
And if you want to do that, then you want someone to tell you, are you going to be able to see one? So what you want to do is simulate the neutrino distribution at late times and see, do any of them actually end up in the Milky Way?
Yeah.
Because they could be spending billions of dollars on something that maybe we find out neutrinos don't even come here at all.
Yeah.
So
I don't know anything about this. Like, what do we expect? Should we be able to find a neutrino background or?
I think everyone expects it to. Like,
right.
Naively, there's no reason for you to think that neutrinos don't get captured in something so big like the local group.
Right.
But would they exactly where they end up? That's actually something that we want to do next.
Okay.
So I can't tell you anything right now because we don't know. But
yeah, sure.
It is something that's worth looking into because there are experiments that immediately will benefit from it.
Yeah, I guess that's sort of a good segue into the last bit, which is sort of on a broader scale. Like, what would you say is the impact on the wider field from this sort of paper? You know?
What we do is mostly a proof of concept because we don't have any fancy big supercomputers in UNSW.
Yeah.
So these papers are not meant to tell people, hey, this is now the best neutrino simulation you can get. It's kind of showing them there are better techniques or like a Swiss Army knife worth of techniques where, depending on your situation, you might want to pick the one that suits you the most. And with like Moore's law coming at the near dead end, then computation power is not going to suddenly explode in the next 10 years. So anything that could save you resources to direct them into something else that you care more about, like say hydrodynamics or just getting the cold matter sector more correct, then it is going to be useful for people that will inevitably run into this resource constraint. So yeah, we're just offering alternate techniques that are very easy to use and are absolutely more than good enough for getting the results that people will care about, and at the same time saving them money and time.
Right, and then I mean, even on the broader again, like, why do I care about these simulations? Why do I care about cold dark matter? What's the like fundamental physics I want to figure out from this stuff?
So the next generation surveys, they look at these kind of like the big large-scale structure distribution, and you can derive from them a lot of fundamental physics like dark energy, equation of state, and neutrino masses and stuff like that. But you need something to compare to because once they take a photo of the cosmic web, they could be anything. So then theoretically you need to have a model that can produce a prediction and then you match the two up and say, does this look like it?
Yeah.
So n-body simulations are the only viable way to get these absolute nonlinear predictions because no perturbation theory could save you from that.
Yeah.
So if we want to make sense of the next generation surveys like Euclid and LSST, then we really do have to get these n-body simulations done well and correctly, so then we have something reliable to compare to.
Are we on like a time crunch here? What's the projections?
I don't think that much of time crunch. I think it's going to be at least 15 years before we can get anything useful out of that.
That's the prime of our careers, maybe. I don't know.
Yeah, actually. Yeah. I mean, I think we're on the right place.
Well, maybe you. Yeah.
We'll see about that.
And if the viewer was to take like one thing away from this, like what do you really want them to walk away with? Yeah.
I want you to stop being afraid of neutrinos. They're scary, they're hard to deal with, but like there are better ways now, and we're kind of taming the beast one step at a time, I suppose.
Yeah, I guess that's what we're doing in all of science, right?
Yeah.
One step at a time. Yeah. Anything else you want to add?
No.
Yeah. Any questions from the audience? Got some satisfied faces. All right, I guess we'll wrap it up for that then. Thanks for coming all the way out here.
Thank you very much.
Yeah, it was nice. Maybe we'll go for a beer now or something. I don't know.
Oh yeah.
That was the premise of the show originally, but so far we have not had any beers during any of the episodes.
Oh, wow, okay.
Imaginary ones.
Hey, this is a good time to start.
Yeah, seriously. Alright, so I guess we probably won't do any more of these until after the holidays, would be my guess.
True.
So,
2021.
Yeah, see you guys in 2021.
Take it easy. Stay safe.